Hello and welcome to another one of these ADD videos. Today we're going to be looking at an example of Lagrange multipliers, specifically a two-dimensional example. We're going to try to optimize, maximize, or minimize, but restricted by this constraint. So again, we know this is a constraint because it's equal to a number, and you subtract that number over, and then you're going to get g of xy equals that function minus the number. Again, because we have one constraint, we're going to use method 1. In which we're going to find all first order partials, and then after we find the partials, we're going to set up these relationships of fx equals lambda times gx and fy equals lambda times gy. Basically, we're going to do first order partials equal to each other with lambda on the g side. Solve for lambda in each, set lambda equal to lambda, establish relationships, plug into the constraint, solve for the other values, and then plug into the maximum function. Okay, so I went through that kind of fast. If you haven't watched the concept video, go back and watch it. But here was the function. F sub x is equal to 2x. This is step 1, finding all the partials. 2y. Here's the constraint. G sub x is equal to y, g sub y is equal to x. If you don't remember your first order partials or any partials, go back and watch that video and practice before you do these, because it will be next to impossible to understand what's going on otherwise. So then we're going to set 2x equal to lambda times y. That's f sub x equal to lambda g sub x. And then f sub y is going to equal to lambda times g of y, so that would be 2y equals lambda x. And then what was the next step? Solve for lambda in each, so 2x over y equals lambda in the first one, 2y over x equals lambda in the second one. Oops. And then we set lambda equal to lambda. 2x over y equals 2y over x. Multiply both sides. 2x squared equals 2y squared. If you cross multiply, right? Anytime the two fractions equal each other. And then the 2's can cancel out if you divide by 2 on both sides. So we have now established a relationship between x and y. So what we want to do next is we want to solve for that by plugging it into the constraint. So if we plug into the constraint, we're going to end up with, what was this, xy minus 4. Okay, equals 0. So now what we should do is solve for our y or x in our relationship. And we have, let's solve for y. Would equal plus or minus, don't forget when you square root something, x. Alright? So if you plug in a plus x, you're going to get x times x. I'm going to move the 4 on the other side. You get x squared equals 4. So x equals plus or minus 2. Okay? So now that we know one set of x's, let's go ahead and plug them in here. If I plug in a positive 2, I get the point 2, 2 and 2, negative 2. Right? Because y equals plus or minus x. So if I plug in the positive 2 there, I get those values. But then when I plug in a negative 2 for the x value, I get the same y values. Because negative and negative gives me a positive, and then positive times a negative gives me negative. Okay, so these are all our critical values. Again, what I did was plug in positive 2 here, and you get 2 answers, and then plug in a negative 2 in that same place, get 2 answers. So we have our critical points. Let's see what's going on with our function. Our function is f of xy equals x squared plus y squared. So if I plug in a -2, this is for -2, -2. You don't have to do it for every critical number. Hopefully you can see that all these are going to give you the same value because the x's and the y's are the same thing, right? We have whether it's +2 or -2, you're going to get the same answer here, which is going to be 4 plus 4, which is 8. So they all have a value of 8. Now that doesn't really help us because the problem itself didn't specify, or I didn't specify, to either maximize or minimize this function subject to that constraint. So how can we determine it? Well, let's look at some of the graph knowledge that we have. We know that x squared plus y squared, or you should know by now, is a paraboloid bowl. So this thing is going to be bounded by the bottom, but unbounded by the top. So xy equals 4 can go up forever, depending on what x and y are, but because this bowl stops here, we know that these values all have to be absolute mins, subject to that constraint. All of them had a value of 8, so they're all absolute mins. Okay? So practice, practice, practice. You can see it requires a little graph knowledge as well sometimes. Sometimes it'll be clear cut. You'll have 4 distinct points. You'll plug them in. 2 of them, or one of them will clearly be a max, and one of them will clearly be a min. Okay? Other times you have to use a little logic like this. I hope this was helpful. Practice, practice, practice. Make sure you watch the 3-dimensional example video as well as the 2-constraint example video. Thank you and have a nice day.